Hi everyone, it's Coach Fred, and today I'm going to be going over an extension of the rational root theorem. I'm going to be talking about the conjugate root theorem. I want you to remember that roots can be real or imaginary. We talked about that in the past, and they could also be rational or irrational. But another very useful tool for us to find the zeros is called the conjugate root theorem. Basically, we have to remember that conjugate roots come in pairs, no matter what. So the translation to all the book mumbo jumbo is that irrational roots will always come in pairs of conjugates. So remember, irrational roots are any radical that is not a perfect square, or it could be imaginary. So basically it says that if a plus root b is a root, then a minus root b is a root. Remember, these resemble dots, the difference of two squares. All right, so 6 plus root 3 is a solution, then so is 6 minus root 3. If negative root 5 is a solution, then root 5 is a solution. That's what the conjugate root theorem basically says. So you're going to have to remember that, right? Like if you see one irrational root, you need to know that the conjugate is also going to be a root. All right, the same is true with complex roots or imaginary roots. If a plus bi is a root, then a minus bi must also be a root because they come in pairs. All right, so that means if 5 minus 7i is a solution, then 5 plus 7i is a solution. If 3i is a solution, then so is negative 3i. All right, so how do we use this? Well, we could be asked to write a polynomial, okay, or to find two additional roots. So if I know that 2/5, 3 plus root 7, and negative 4i are roots, okay, then I know that there's two other roots, 3 minus root 7 and 4i. So this actually has 5 roots. So it's a degree 5 polynomial. We're going to be able to do more with that. All right, here we've got negative 5, it's a real root. 3, it's a real root. 4 plus 7, I, imaginary root. So I know that 4 minus 7i is also a root. Negative root 17, it's an irrational root. So I know that plus root 17 is also a root. So 1, 2, 3, 4, 5, 6 roots. So I know it's a degree 6 polynomial, okay? All right, so that allows me to actually write a polynomial. I'm going to look at a few examples. We've been able to write a polynomial equation given the roots. Well, if it was 7 and negative 10, I knew those were solutions or roots. I could write the factors. So x minus 7, x plus 10. Okay, so y equals. And then I could multiply that out. Now, that's disregarding the a term, right? For now, we're going to do that. All right, but if I know that 5a is a root, then I also know that negative 5i is a root. So I would write them as factors. So the first one would be x minus 5i, and the second one would be x minus negative 5i, which becomes x plus 5i. If I multiplied those out, remember, they're conjugates, so we don't have to FOIL or multiply the whole thing. We only have to multiply the first to the first and the last to the last, giving me x squared minus 25i squared. I know you all remember at this point, I squared is negative 1, so this becomes x squared plus 25. Y equals. And there is our polynomial function. Also could write it as p of x equals x squared plus 25. All right, so that's the conjugate root theorem. We're going to look at the harder examples in class tomorrow, but hopefully that was a helpful start. Have a great night.